In this segment, we're going to take a look at predicting new observations using a fitted linear regression model in R, as well as how to carry out f-tests, even though I don't usually recommend that you actually use them. And finally, how to make some beautifully formatted regression tables using the model summary package. We're going to start off with predicting new observations, and we're going to start off with the function that is aptly named predict. This is a base R function that you can use to make predictions from a wide variety of fitted models beyond linear regression. But for today, we're going to content ourselves with predicting from an LM object, so a linear model. The help file for this function predict can be found by typing $predict.lm in the console. And the basic syntax is predict, then the name of some object that is a fitted model, and then a new data object. So new data is going to be a data frame of the new observations that you want to predict. So in linear regression, it's going to be the x values at which you want to predict y based on the fitted regression. So new data must be a data frame, and we know that a tibble is an example of a data frame, so that's fine. The columns of new data must have names that match the names of the regressors from the fitted LM object that you passed into predict. So for example here, continuing our kid score example, that fitted regression has a y variable kid score, and then x variables mom IQ and mom education. So this syntax says that we're fitting a model that includes both of those variables and their interaction. That's what the multiplies sign means in an R formula. So if I want to predict at some new values of those x variables, I'll create a data frame here. I could have created a tibble too, but just for fun, I'll use the data.frame function. And I'm going to set up a named column mom IQ, where I'll put in three values, 100, 120, and 80. And then mom underscore education. So these have values no HS, HS, and HS in keeping with the example that we've been working on. So you can see this new underscore kids data frame. It has two columns, and their names exactly as they should be. So when I pass this in, for every row of new kids, I've got x values, and I'm going to push them through the fitted regression to get y values. So in the final line of R code on this slide, I'm getting three values. These are the fitted y's that correspond to those three rows of x values. If you don't specify the new data argument to predict, you'll still get something. And what you'll get is, in fact, the fitted values from the regression. In other words, if you don't tell predict otherwise, it's going to evaluate new data at the same data frame that you used to fit the original regression. And on this slide, I have one line of code that just shows you that's the case. I'm using all equal to test whether predict reg1 and fitted.values reg1 are all identical. Well, not all identical, whether they are all equal up to numerical precision. I should just clarify that all.equal does not test for exact equality. It tests for approximate equality up to machine precision. And indeed, these are the same. But that's not the only way we can get predictions out of a fitted regression in R. We can also use the function augment that we've already met from Broom. And this is actually a superior option because we know that Broom gives us some improved functionality over the base R functions. The way that we use this augment command is almost exactly the same way as we did predict before, in that we're going to specify a fitted model, and then we're going to specify new data in the same way that we did before. The difference here is that the fitted values won't just be returned, I should say the predicted values won't just be returned as a vector. They'll be returned attached to the new data frame of x values that you supply. And this is actually kind of sensible. We'd like to see for each of the x combinations that you pushed in, what are the predicted y's, and that's exactly what this gives us in a nice handy format. Now notice that the column name that it uses for the predictions is .fitted. We may wish to rename this for clarity in our example. So in this case, what I've decided to do is rename that kid underscore score underscore pred. So our prediction of kid score. And if you want some more details on this function, you can take a look at Broom help file for augment.lm. So again, this augment function is actually a method that can be applied to lots of different fitted model types. So it can be applied in particular to a linear model. And if you look up the help file for augment.lm, you'll be able to figure out exactly how it behaves when applied to a regression model. Because as we talked about, these functions from Broom, they behave differently depending on what sort of model is passed in. They know how to do the right thing. Just like if I tell you to eat, you know that you should use one procedure when you're given ice cream, namely eating it with a spoon, and a completely different one if you're given a steak, cutting it with a knife and fork. Similarly, Broom Augment will know how to deal with an LM model differently from, say, a GLM model. All right, so that's enough about prediction. Now, sometimes you may want to carry out a hypothesis test of a linear restriction. More about whether that's a good idea in a moment, but first let me explain what I mean. So the regression output that we've looked at so far gives us estimated coefficients and standard errors. So if you wanted to produce confidence intervals for any of the individual regression coefficients, that's straightforward with the standard errors. And if you wanted to carry out a test, you could similarly do so using the same standard errors. But sometimes you may have a more complicated hypothesis test that you want to carry out. For example, you may want to test some kind of a restriction on the regression function. And this restriction might take the form of some matrix R multiplied by the parameter vector beta being equal to some vector Q. So we might be testing the null hypothesis that R beta is equal to Q against the alternative that it's not. So what form might this take? Well, we might be testing that one component of beta is equal to another, or that a number of coefficients sum up to 1, or perhaps that one of them is 0 and two others are equal to each other. And you can actually carry out a test like this merely by using the standard error from the regression output. It only allows us to test linear restrictions of the form one coefficient equals one particular value. Now, if you want to do this, you can use the package you can use the package car and the function linear hypothesis. If you have no idea what I'm talking about when I mention an f-test, you can visit this fantastic blog to which you should all subscribe and all be reading that will explain the basics of an f-test. But for now, I'll take that as read. And I want to give you a word of caution. Null hypothesis significance testing is, in my view, almost never the right tool for the job in applied work. I'm showing you this f-test not because I think it's important, but because by popular demand, people want to know how to do it. Testing is rarely the right tool for the job. P-values are very frequently misunderstood and misinterpreted, and indeed, there's even an official statement by the American Statistical Association warning you against their misuse. You should take a look at that. I'm going to have more to say about this in a future lecture, which I have humorously entitled Statistical Inference Defense Against the Dark Arts. And if that's not enough, you should probably check out this fantastic teaching note by Cosma Shalizi that explains to you why not only an f-test is a bad idea, but r squared is totally meaningless and useless. Sounds a bit over the top, but I think that that is actually a correct interpretation of both of those things. They're just a distraction at best. However, for the sake of completeness, I am going to show you how to do these f-tests. And to keep life simple, I'm going to assume homoscedasticity. In a future lecture, we'll talk about inference when you're not willing to assume that the error variance is unrelated to the regressors. So with that huge disclaimer out of the way, suppose we wanted to test the not terribly interesting and not terribly meaningful hypothesis that beta naught and beta 1 are both equal to 1. In other words, that the regression intercept and slope are both 1. Now, in this particular regression, that doesn't make any sense, but it's just an illustration. So the way that we use this linear hypothesis function is first we've got to load the library car, and then we specify the test as follows. Linear hypothesis, and then we write down the name of the fitted model object, reg1, and then we specify a vector. In fact, it's a character vector. The form of this vector is the name of each of the regressors. So these refer to the names in the model that you fitted. And then a way of representing the restriction. So here, the restriction is that each of them is equal to 1. So the character vector says name equals 1. And since one of those is the intercept, it's not actually one of the regressors, we denote it by parenthesis, capital I, intercept, and then another parenthesis. In other words, we're matching the names to the regression output that we would see, for example, if we typed in reg1 after running it. And you can see that when you do that, you get the p-value for the test and some other information, such as the degrees of freedom and the F statistic. There are actually different variants of F-test. So one variant, and this is in fact the default, is the F-test that assumes that the error terms in the regression are in fact normally distributed, in which case the F-test is exact, and we actually compare the F statistic to the finite sample F distribution. So the F distribution is to the chi-squared distribution as the t distribution is to the normal. So in a sort of a small sample setting, the t distribution differs from the normal. When the degrees of freedom are small, the two disagree. The same is true for this F distribution relative to the chi-squared. But if you want to instead compare your F statistic against the asymptotic distribution, in other words, against this asymptotic chi-square, you can do that. All you've got to change is add the option test equals, quotes, chi-squa to linear hypothesis. All right, I've got an exercise for you just to make sure that you understand how these F-tests work. Not that they're very important, but again, merely for completeness. And I think at this stage, it would be a good idea to pause the video and try them out. As usual, the solutions and explanations are available on the course website, detralia.com/ERM. All right, welcome back. We're now going to finish off this lecture by showing you something that is much more useful than F-tests, namely how to make really nice regression tables very easily. So we have seen in a past lecture how to use the function data summary skim from model summary. Today we're going to learn, I should say, how to use the eponymous function model summary from model summary to make some lovely regression tables. So above, you ran these regressions as part of one of the exercises. I'm going to give them names. Reg underscore pooled, reg underscore high school underscore dummy, and reg underscore interact. Please observe, I am using meaningful labels here. This is important. We want to use meaningful labels so we know what we're talking about. Also, when we make tables, we really don't want to report an insane number of decimal places. If your standard error is 2 and you show me 7 decimal places, you're just polluting your table with noise. None of those decimal places are actually meaningful, so let's leave them out. And it's also a bad idea to report millions of meaningless goodness of fit measures. Nobody reads those things anyway, so I'm going to get rid of them. Here is my first example. It's the simplest one. I'm going to use the library model summary. I've got to load it using this library command. And then I'm simply going to use model summary reg pooled. This prints out a big table with lots of stuff I don't want. Too many decimal places, tons and tons and tons and tons of goodness of fit statistics like R squared adjusted, AIC, BIC, log likelihood, and so on. But fortunately, we can get rid of these. So let's do that. And let's also add a table and some notes. All right, here we go. Now things are starting to look good. So I'm going to use the option GOF omit. That stands for goodness of fit omit. And I'm going to type the names of the goodness of fit statistics I want to omit, followed by a little bar. So the bar separates the ones that I want to remove. So I'm getting rid of log likelihood, R squared adjusted, AIC, BIC, and F statistic. The next option I want you to take a look at here is FMT. That stands for format. FMT equals 2. That says only give me 2 decimal places. And then finally, I have the ability to specify a title and also the ability to specify notes. Maybe this hits a bit too close to home for some Harvard Business School professors who I won't name for fear of being sued. But in this case, the data were not actually fabricated. I'm just pulling your leg. But notice we've got a much nicer, much cleaner regression table. And indeed, 2 decimal places are probably well, 2 decimal places might not be overkill here. In fact, I take that back. This standard error is actually 0.06, so it's not crazy to present these 2 decimal places here. For the intercept, with a standard error of 5.9, it's probably overkill, but we're using the same number of decimal places for everything, which is simpler. Unlike r squared, which is almost always useless, I should just point out that the root mean squared error, sometimes called the standard error of the regression, is a very useful quantity. This tells us, on average, how accurately the regression is predicting in sample. So this value of 18.22 tells us that, on average, this regression using MomIQ predicts kid test score to an accuracy of about 18 points, which isn't bad. All right, but what you really want to do is make one of those cool regression tables like you see in all the top applied journals, right? So here what I'm going to do is I'm going to construct a list with 3 elements: reg pooled, reg HS dummy, and reg interact. These are 3 of the regressions that we fitted above. When I construct this list, I'm going to call it kids_regressions. I can now pass the whole list in as the first argument of model summary. And what do you know? I get this beautifully formatted regression table that lines everything up nicely. So we can see how the estimates change as different regressors are added to the regression. And the titles up at the top are not that interesting. They're just 1, 2, 3. But if you want these to be different, what you can actually do is you can construct a named list where you give these reg pooled, high school dummy, and interact names. If you do that, then the names will appear at the column headings. So that's it for linear regression. I hope that you've enjoyed the ride. Look forward to much more fun with model summary in the future, and much more fun with fitting models other than linear regression. In future lectures, we're going to be taking a look at generalized linear models and instrumental variables, among others.